Let's learn more about the cross product. There are several properties for the cross product, and these properties can easily be seen by simply writing these out with their components by definition. So if we have vectors a, b, and c, and then we have a scalar c, if we cross a and b, that equals the negative of b cross a. And we saw this in the last video. If we have A cross A, first of all, A and A would be parallel vectors, and parallel vectors have a zero cross product. But we could set this up with a determinant, and when we did those smaller determinants, we would always get 0. So it's easy to write these out and see why these would be true. And here, if we have a scalar, we can multiply the scalar to one of the vectors first and then do the cross product, or we can do the cross product and multiply the scalar later. Again, easily seen by writing these out. This one basically says that we can distribute this cross product across addition here, and there's a couple of ways that it can be done. Now, this one, it maybe is not as intuitive, that if we dot A with B cross C, we get the same thing as if we do A cross B and then dot C. And a write-up of number 6 will follow this video. And 7 maybe is not as intuitive either, and it says that if we take A crossed with B cross C, it's the same thing as A dot C times B minus A dot B times C. And again, following this video, there will be a write-up of writing these out with their components and showing you that 7 is true. Now let's look for a minute if we cross the unit vectors. So if we have I cross j, we have I, j, k, and I would be 1, 0, 0, and j would be 0, 1, 0. And you can see when we do this cross product that for I, if we cross off its row and column, we get 0 and 0. And then negative j, and we get 0 and 0. And then for k, we get 1. So when we do I cross j, we get k. If we tried j cross I, we write I, j, k. J is 0, 1, 0, and I is 1, 0, 0. You can see when we do this, if we cross off i's, we get 0, 0. Negative j, we get 0, 0. K, we get 0 and negative 1. So this will equal negative k. And that would make sense because we already knew that if we tried to commute these, that it equals the negative. Now let's go ahead and do k cross I. So we have I, j, and k. And for k, we have 0, 0, 1. And I, we have 1, 0, 0. And when we do the I, you see we get 0, 0. We do negative j, and we get 0 and negative 1. So that will be j. And then we do k, we get 0 and 0. We could continue to do this, and we would find these. So we do I cross j will equal k. If we did it in the other order, it would be negative. J cross k equals I. K cross j equals negative I, and so forth. Now we can kind of remember this as we can put them in a circle with I, j, and k, and if you go clockwise and you cross, you get a positive, and if you go counterclockwise and cross, you get a negative. So in other words, if I did j cross I, it would be negative k. If I wanted k cross I, it would be j. So depending on the direction, positive or negative. Now, a couple other interesting things and things to watch out for. We know that the cross product is not commutative because when we turn those around, it's the negative of that. But another property that we often take for granted that does not apply to the cross product would be what if we tried associativity. So if we had I cross j, if we did I cross j first, that would be k, and I cross k, that is negative j. But if we did I cross I first, that's 0, and 0 cross j would be 0. So it is not associative. The cross product across 3 vectors is not associative. Now let's look at 2 vectors, And if we extended and made this into a parallelogram, we could drop this down and we'll have this angle theta. And we could figure out the height of this parallelogram by using trig. So we would have sine theta equals the height over the magnitude here, so over the hypotenuse. And so we could solve this for the height, and it would be the magnitude of b sine theta. We know that the area of a parallelogram is the base, so that'd be the magnitude of a multiplied by the height, which is the magnitude of b sine theta. But oh, look at that. That is just the magnitude of the cross product. So the length of the cross product is equal to the area of the parallelogram determined by those vectors a and b. Now, if we take the product A dot B cross C, is called the scalar triple product of the vectors A, B, and C. Because when we cross these two vectors and we get a vector, but then when we take this vector and we dot it with another vector, we will get a scalar. So this scalar triple product is a number. Now, one way we could express this is if we set up a determinant, instead of having our ijk here, after we get this vector, we are going to dot it with a, so we could put the components of a here, and when we compute this determinant, we will have this scalar triple product. Let's see an interesting application of this. If we start with the vectors b and c, and we make the parallelogram defined by those, we know the area of that parallelogram is magnitude of vectors b cross c. Now, if we look at that geometrically, we know that that cross product is a vector that is orthogonal to both b and c. Now let's take a vector A and let's put in the pieces to this. This is called a parallelepiped, and we are going to figure out the volume of this parallelepiped. And the volume would be the area of the base and then multiplied by how high this is. Well, we can get how high this is looking at the height right here. We could figure that out using right triangle trigonometry again, because we're after this piece right here. And so we can see that with this angle, that would be adjacent over hypotenuse, and we could solve then for that adjacent side. So we would have the magnitude of a cosine theta. Now we're putting absolute values on the cosine theta because we're going to make sure that this is positive. And now that we have the height, we can take this height and multiply it by the area of this base to have the volume. So volume is area of base times height, so that's going to be b cross c times magnitude of a cosine theta. But what is this? That is just simply the definition of the dot product between these two vectors. So we could express this volume of this parallelepiped that was determined by this A, B, and C as the magnitude of their scalar triple product. So this is just A dotted with B cross C. One other application involving the cross product is the torque. Think about what variables help that twisting power when you try and loosen a bolt and you have this wrench. As we look at this, the magnitude of the force that you apply will be a piece of it. The length of the wrench would be a piece of it, and then the angle at which you're applying the force will also be a piece of that. So as we look at that, that force is not applied in exactly the right direction, so we would need to go ahead and look at the component of that that is perpendicular. And we could figure that out with our right triangle trig, and that would be the magnitude of F sine theta here. If we wanted to compute the torque then, the torque is actually R cross F as we look at this, and we can express the magnitude of that torque then as the magnitude of R times the magnitude of F sine theta.